In lab, you guys were looking at impulse and momentum. And impulse is really just a change in momentum. It's caused by a force. So if we start with Newton's first law, what we have is net force equals mass times acceleration. Doing a little rearranging, we can put that in terms of momentum, and we get net force is equal to the change in momentum, delta P, divided by time. If we multiply both sides of this equation by time, what we get is the change in momentum is equal to force times time. Now remember, change in momentum is equal to mass times change in velocity as long as the mass isn't changing. So really, what we can do with this equation is we can figure out the change in velocity if we want as a result of a force that acts. Now the quantity net force times time is called impulse, and it causes that change in momentum like I said, but it has different units than momentum at face value, right? Force times time is newtons times seconds. Well, a newton is the amount of force required to accelerate 1 kilogram or meter per second per second. So if I take a kilogram meter per second squared times a second, this cancels that second, and I'm left with kilogram meters per second, which, as you recall, is the unit of momentum. So impulse and momentum kind of go together. Impulses cause a change in momentum, and if we know how big the impulse is, we know how much the momentum changed. Now you guys did two different things in lab. You did one thing where you had a cart hooked to a spring, and that spring stretched out and it caused the cart to stop moving this way and start moving this way. So it caused a force that acted over time. So we had an impulse, but we got a force time graph from that looked like this. Okay? Now, because impulse is equal to force times time, we should be able to find the area of this graph. This is zero force. This is my time axis down here. We should be able to find the area of this graph, and that should give us the impulse. The problem is this graph doesn't have an easy area to calculate. It's not a triangle. It's not a rectangle. So we had to figure out a different way to get the area of that graph. So I'm going to draw this a little bit nicer. And we see if I have a force time graph that looks like this, how can I get the area under that graph? Well, in calculus there's a method called an integral where you can actually calculate the area under this graph. We don't do that. Instead, what we're going to do is we're going to use an average. Okay, because it's got a maximum force up here but a continually changing force. So if we take this time interval from here to here where the force is non-zero, so this would be T1 and this would be T2, and we say the average force, and the technology exists for us to get that, is about right here. Okay? And that means we could think about this shaded region, and then these two things, if you think about them rotating down to fit underneath over here, it gets us this rectangle. So this is average force. And now I actually can multiply the average force times the delta t, times the duration in time, F delta t, and that's going to get me my impulse. So when we do that, when we find the average force and multiply it by time, we get the impulse acting on the object. And what you guys saw in lab, and you verified hopefully, is that yes, impulse, F delta t, is equal to change in momentum. Now the really cool thing about that is we can have an object undergo a change in momentum, and we can have a really big change in momentum with a really big force, or a really big change in momentum with a really small force. So when you guys used the cart and you pushed it, you saw a force time graph that looked like this. But then you changed the cart to having a clay bumper and you got a force time graph that looked like this. Okay? Even though the carts underwent similar changes in momentum, they had entirely different force time graphs. And the reason for that is when you have a clay bumper, it collapses a little bit and stops the cart, which means it's got to exert a big force over a very small amount of time, whereas the spring could stretch way out and it could exert a much smaller force over a much longer time. So impulse momentum is actually all about how to increase the duration of a collision so that the force can be smaller, or if you want to have a sharp tug on something and really get it moving quick, then you need a big force over a small time to cause an equal change in momentum. So when you work an impulse momentum problem, what you got to realize is small forces can cause big changes if they act over long times. And similarly, big forces can cause small changes if they act over very short periods of time. A bungee jump, where you have a bungee cord that stretches out, that's so you don't have a sudden stop at the end. It's so you slow down over a long period of time. A seatbelt is designed to keep you in your seat and slow you down as you move forward and then brings you back, as opposed to you flying into a dashboard, which doesn't slow you down suddenly, slowly. It slows you down suddenly to a much bigger force. So the impulse momentum theorem allows us to go with, or the impulse momentum relationship allows us to figure out how much force can act over a certain amount of time to cause a given change in momentum.